Platinum is so rare that every ounce ever mined could fit inside a single living room. Yet this elusive metal powers billion-dollar industries and graces the world's most coveted jewelry. Refining platinum to 99.95% purity happens inside hidden, high-security facilities, far removed from the glittering surface the world sees. For every ton of rock blasted from 1,000-meter shafts, miners recover just a few grams, making platinum over 30 times scarcer than gold and dependent on a single region for most of its supply. If you've ever wondered how such scarcity transforms into nearly flawless bars, the journey inside these secretive refineries reveals a story more demanding than you'd ever expect. The stakes for energy, industry, and luxury all start here. Every year, just 170 metric tons of platinum leave the world's mines, less than the weight of a single Boeing 747. Nearly 3/4 of that total comes from a single geological feature, the Bushveld Igneous Complex, a vast formation buried beneath the grasslands of South Africa. This region, stretching for hundreds of kilometers, holds the richest known platinum reserves on Earth. South Africa alone produces around 120,000 kilograms annually, making it the undisputed leader in global supply. Russia's Norilsk region and Zimbabwe's Great Dyke add smaller but vital contributions, while North America and other sources barely register on the global scale. Unlike gold, which sometimes forms thick veins, platinum is scattered in tiny pockets, mixed with other metals. For every 30 ounces of gold pulled from the ground, miners find just 1 ounce of platinum. All the platinum ever extracted would fit inside a single living room, a volume so small that it seems almost impossible to support entire industries. This scarcity means that a single disruption in South Africa can ripple through global markets, sending prices soaring and factories scrambling for alternatives. The world's reliance on one region and the razor-thin margins of supply create an economic tension that underpins every gram refined. Platinum's story isn't just about rarity. It's about how the world's appetite for energy, technology, and luxury depends on a metal that is both precious and perpetually at risk. Beneath the grasslands of South Africa, platinum mining plunges over a kilometer underground. These shafts cut through ancient rock, sometimes reaching depths greater than 3 Empire State Buildings, stacked end to end. Inside, the temperature and pressure climb, and every meter of descent means greater risk and complexity. Miners and machines work in narrow tunnels, following seams of ore just centimeters thick. Each blast and haul brings up rock that, on average, contains only 3 to 7 grams of platinum per ton, less than a sugar packet scattered through a truckload of stone. Once at the surface, the ore faces its first transformation. Massive crushers pulverize the rock, reducing boulders to gravel in minutes. Next, powerful mills spin and grind the fragments into a fine powder, freeing the tiny platinum particles from their mineral cages. The result is a gray slurry, thick as wet cement, ready for the next step. Froth flotation begins as air bubbles and chemical reagents are injected into tanks. Platinum-bearing particles cling to the bubbles and rise, forming a shimmering froth at the surface. This concentrate is skimmed off, while the waste sinks and is discarded. Even now, the precious metal is measured in grams per ton, still a far cry from the purity required for the market. The concentrate, loaded with platinum and its sister metals, is now ready to enter the smelter, where fire and chemistry will begin the process of true separation. Inside the smelter, heat reigns supreme. The concentrate, thick with platinum and other metals, is fed into a submerged electric arc furnace. Graphite electrodes, each as tall as a person, channel thousands of amps into the heart of the charge, pushing temperatures above 1,500 degrees Celsius, hotter than molten lava. Here, the ore transforms. Silica fluxes blend with the molten mass, coaxing iron and unwanted elements into a glowing river of slag that floats to the surface. Technicians monitor the color and flow, ready to adjust power or flux if readings stray from target. Every few hours, a tap hole is opened. Molten slag spills away, leaving behind a dense metallic layer called matte. This matte holds platinum, palladium, and other precious group metals, now separated from most impurities, but still far from pure. Next, the matte is transferred to the converter. Here, air and oxygen are blasted through tuyeres, sparking a chemical battle. Iron oxidizes first, captured by silica to form more slag. Then sulfur burns away as a choking gas. The superintendent, face shielded against the glare, watches as the matte's color shifts, a sign of rising purity. Timing is critical. Too long, and precious metals are lost to the slag. Too short, and impurities remain. The result is a refined matte, rich in platinum group metals, ready for the next stage, chemical dissolution. In this crucible of fire and control, the journey from rock to rare metal crosses its first threshold. Inside a sealed laboratory, the chief metallurgist stands behind glass, monitoring a process that relies on chemistry as much as engineering. The matte, still laced with traces of nickel, copper, and other precious group metals, is first treated to remove base metals. What remains is a residue, dense with platinum, but still tangled with impurities invisible to the naked eye. Now comes the most delicate phase: dissolution in aqua regia, a potent blend of hydrochloric and nitric acids. This mixture, heated to just the right temperature, breaks down the platinum into a solution, leaving behind less soluble metals for separate recovery. Every step is measured in milliliters and minutes. Fumes are drawn away by powerful scrubbers, and each batch is tracked by barcode and logbook. Selective precipitation follows. Ammonium chloride is introduced, coaxing platinum to form distinctive yellow crystals of ammonium hexachloroplatinate. These are filtered, washed, and gently dried, with technicians inspecting each batch for color and clarity, signs of purity at the atomic level. The dried crystals enter a high-temperature furnace, where they are calcined at up to 1,000 degrees Celsius. The result is a fine, gray powder, known as sponge platinum. Only now does the metal approach its final form. At nearly 1,700 degrees Celsius, the sponge is melted in an induction furnace. The chief metallurgist checks the readouts as the platinum liquefies, then cools into solid bars or sheets. Each ingot is weighed, labeled, and set aside for the next round of analysis. In this room, chemistry is not just a science. It is an act of precision, transforming a stubborn ore into platinum that is 99.95% pure. Inside the analytical suite, the laboratory manager oversees a process defined by precision and protocol. Each platinum bar is sampled and tested by both in-house and independent laboratories, following the dual assay rule set by the London Platinum and Palladium market. Using techniques like ICP-MS and XRF, these teams confirm that every batch meets the strictest international standards. Only after both labs agree within a fraction of a percent are the bars cleared for release. Most of these bars are destined for industry, fuel cell stacks, catalytic converters, and medical devices, while a smaller share is allocated to jewelers. This rigorous verification ensures that every gram entering the market is backed by certified integrity, with a clear record from mine to final application. Inside a dedicated recycling bay, a senior engineer oversees the arrival of spent catalytic converters and industrial scrap, each one a hidden reservoir of platinum. Specialized shredders and chemical baths break down these components, releasing platinum group metals for recovery. Closed-loop refining systems reclaim up to 95% of the precious metal, using only a quarter of the energy needed for mining fresh ore. This secondary supply now accounts for a growing share of the market, softening the industry's environmental footprint. As demand for hydrogen fuel cells and green technologies accelerates, Recycling isn't just a cost-saving measure. It's essential for meeting future needs without depleting the planet's rarest resources. Every year, the world produces just 170 metric tons of platinum, less than would fill a living room, with over 70% of it coming from South Africa's Bushveld Igneous Complex. This documentary traces platinum's journey from ore buried more than 1,000 meters underground, through smelting above 1,500 degrees Celsius, to chemical refining with aqua regia and final casting at 1,700 degrees. Each bar is independently assayed before entering markets where more platinum is used for catalysts and medical devices than for jewelry. While closed-loop recycling now recovers up to 95% of used platinum, deep mining and high-energy demands still drive environmental concerns. Key details of site operations and security remain classified, and the full impact of future demand for hydrogen technologies is not yet known. The documented facts show platinum's path is shaped by scarcity, exacting processes, and global industry standards. Today, every refined bar reflects decades of technical progress and the ongoing balance between supply, demand, and sustainability.